Hello and welcome to Office Hours. This is Office Hours for Chem 400 at FLC. As always, I am ready and looking forward to answering any and all questions you can throw at me. In the absence of questions, I'm going to, check emails, do professor-like stuff. But if you're here and you're live, your questions will have priority. So hit me with them as you have them. Let's see. Totally, dude. I can totally hit up test questions. Okay, cool. Let's start this business. Of course. All right. All right, so here is our first example. So hydrogen represents 25.13% of a molecule's mass. The chemical formula for this molecule is CzH4. Determine, well, oops, let me make this a little determine the value of Z. All right, okay, so you know the problems where you're given the percent composition of each element in the molecule, and you've got to determine, you know, the empirical formula. This is essentially that's exact and same smashed into one. That exact problem, that same problem, but just kind of written in reverse. So if you take a look at this situation, so we are given, oh, and we're also given the atomic masses of hydrogen and carbon. All right, so we're told that hydrogen represents 25.13% of the total mass in the molecule. That means carbon is 74 point, what's that, 87? Let me double check, just because I don't trust my head to do arithmetic, which is sad, granted. 100 minus 25.13. Yep, 74.87% is carbon. All right? Now, excuse me. The mass that represents 25%, i.e. hydrogens, is 4 times the mass of hydrogen, right, which is 1.008. The mass that represents 74.8% is Z, right, however many carbon atoms we have, times 12.01 AMU. All right, so if we set this up, give me 1 second, we can set this up as follows. We know that the total mass of this molecule is Z, the number of carbon atoms, times 12.01 plus 4 times 1.008, right? Because this is the mass of all the carbon atoms in this molecule, and this is the mass of all the hydrogen atoms in this molecule, right? So this is our total mass for the entire thing. We also know that the total mass times 25% or 25.13 over 100, right? Because this is, oops. That's 25% right there, or I should say 25.13%. The total mass times 25% is equal to just the mass of hydrogens, 4 times 1.008, because hydrogen is 25% of the total mass. If we divide both sides of this equation, or here, just going to scoot this over a little bit. something you can't really do with a whiteboard. I'll definitely miss when school is back in session. If we multiply this side of the equation, or both sides of the equation, excuse me, by 100 over 25.13, you'll notice that we isolate total mass on one side of this expression. In other words, the total mass of this molecule is equal to 4 times 1.008 times 100 over 25.13. And we can calculate the total mass by multiplying all these things together. And if I couldn't subtract 25.13 from 100 in my head, I'm definitely not going to try to multiply all these together in my head. So 4 times 1.008 times 100 divided by 25.13 means that the total mass of this molecule is, let's see, we got 4 sig figs here, so 16.04. The number keeps going, 5, 6, 8. But we're limited to 4 sig figs. Here's why this is significant. Now that we know our total mass, we can plug in that value here. And now that we know our total mass, the only variable in this equation is z. So now that we have total mass, we can solve for z. So I'm going to open up a new slide and we are going to do just that. So we solved for our total mass, which was 16.044568, but we only have 4 sig figs. I'm just waiting to round to the very end, is equal to z times 12.01 plus 4 times 1.008. Let's multiply 4 times 1.008. So this right here, so 16.044568, again, 4 sig figs in this number, is equal to z times 12.01 plus, these multiplied together comes out to be 4.032. We need to isolate z, so we're going to subtract 4.032. Oops. Minus 4.032 from both sides of this equation. $16.044568 minus 4.032 comes out to be 12.012568, which equals z times 12.01. And now we can solve for z by dividing both sides by 12.01. .01 cancels, and the value comes out to be 1.0002138, limited to 4 sig figs though. This just comes out to z equals 1. And actually, this is one where you don't need to put decimals because in the original problem, you'll remember we're trying to find the chemical formula for CzH4. And your subscripts in chemical formulas never have decimals. They're always integer values. So z equals 1 for that problem. So quick question, does this new problem ask you to determine the atomic mass of the element? Ah, okay, awesome. All right, so let's see. right, so an element has two isotopes. The first is 91.79 AMU. The second minor is 90.77 AMU with a percent abundance, or I should say with a 21.60% abundance. All right, we've got to find two things. First, the percent abundance of the major isotope, and two, the atomic mass of the element. Starting with the percent abundance of the major isotope, we know that this is going to be equal to 100 minus the percent abundance of the minor isotope, right? Because we're told that there are two isotopes. So the percent abundance of the major is going to be 100 minus the percent abundance of the minor. I think it's 88.40, but let's see. Oh, this is why I punched it in my calculator. It's 78.4. So the percent abundance has of the major isotope, excuse me, is 78.40%. All right, so that is the percent abundance of our major isotope, and we are going to need that value to solve for, to find the atomic mass. Now that we have the percent abundance of the major isotope, we can determine the atomic mass of this atom, because we know that we have to take a weighted average. So our atomic mass will equal the percent abundance times the atomic mass of the major plus the percent abundance times the atomic mass of the minor. All right, that is how you calculate atomic mass. So let's go ahead and take our major isotope, whose atomic mass is 91.79 AMU, and we need to multiply this by our percent abundance, 78.40 over 100, because that's how you, whenever you multiply a number by a percentage, you always do the percentage over 100. And we're going to do the same thing with our minor isotope, which is 90.77 AMU times its percent abundance, 20.60 over 100. So we've got some numbers to crunch. So we've got 91.79 times 78.4 divided by 100. This comes out to be 71.96336 AMU. Sig figs wise, we're limited to 4 by both our percent and our atomic mass of our isotope, so this number has 4 sig figs. Now, for our second, we've got 90.77 times 21.60 divided by 100. This is 19.60632 AMU, and again, we are limited here to 4 significant figures. Now we have to add these together to find the atomic mass of our element. So we got to add these up. So my calculator is telling me that the sum of these two numbers has a value of 91.56968. However, our last significant digit for both of these numbers is in the second decimal place, so we have to round to the second decimal place, and 9 rounds up. So this is going to come out to be 91.57 AMU. Alrighty. So we're told an ionic compound. It's possible. And I guess we'll find out one step at a time. An ionic compound contains 1.73 grams of chromium and 1.60 grams of sulfur. We're told to determine the empirical formula. All right, so just by way of kind of review, the empirical formula is going to have chromium X, sulfur Y, where these values right here, X and Y, are the simplest integer ratio. I should say simplest integer molar ratio. So it's going to be the simplest integer ratio for moles. So first, we got to figure out how many moles of chromium, how many moles of sulfur we're dealing with. So X is going to be equal to 1.73 grams of chromium. Sorry, remember to put that R there. Times, we need to convert grams of chromium to moles of chromium. We have to do the same thing with sulfur. We take our mass of sulfur, moles of sulfur, put grams of sulfur in the denominator. I happen to know the atomic mass for sulfur off the top of my head. It's 32.07. I need to look up the atomic mass for chromium. Let's see. Chromium. Here we go. 51.996. All right, so we have 1.73 divided by 55, oh, not 55, 1.73 divided by 51.996. So this is 0.033, we'll call it 27. Moles of chromium. Let's see, for sulfur, 1.60 divided by 32.07. This comes out to be 0.04989 moles of sulfur. All right, so now that we have these values, we can plug them in as the values for our empirical formula. So chromium, we plug in the molar value 0.03327. Sulfur, we plug in the molar value 0.04989. 8, 9. Now, this is not the empirical formula for our compound because these are not integer values yet, but this is the correct ratio. So we just have to find what integer values go here without changing the ratio. To do this, you can manipulate these numbers by dividing both of them or multiplying both of them by the same thing. And the first step is you want to divide them both by the smaller of the two values. The reason for this is when you divide 0.03327 by itself, it'll come out to be 1. So this is now chromium with a subscript of 1. That's definitely an integer. Let's see how sulfur comes out. So 0.04989 divided by 0.03327. This comes out to be, oh yeah? 1.4995, i.e. 1.5. Now, the way to move forward here is to rewrite this decimal as a fraction. 1.5 is 3 over 2. So if you write this as chromium 1, sulfur 3/2. Again, we know we can't have fractions, but we can get rid of this denominator by multiplying both of these by 2. And now we have our simplest whole number ratio. We've got chromium with a subscript of 2, sulfur with a subscript of 3, and that's the business. Ah. Totally. With these problems, the decimals definitely mean something. So you've got to, convert the decimal to a fraction, then get rid of the denominator. If it was like 1.98 something, that's one that you round. But if it's around 0.5, 0.75, 0.25, those are all meaningful decimals, 0.33, 0.66, etc. Dude, you are so totally welcome. Thanks for dropping by. It's always fun to get some live humans in office hours. Here, let me open up a new slide. All right, so we have a molecule that is composed of, let's see, 80.21% carbon, 10.18% oxygen, and 9.61% hydrogen. By mass, has a molecular weight of 314.47 AMU. Identify the correct empirical formula for this molecule and the molecular formula. So first off, to calculate the empirical formula, so we're going to need the simplest whole number ratio for each element, and we're going to assume that we have 100 grams. If we have 100 grams, that means we'll have 80.21 grams of carbon, 10.18 grams of oxygen, and 9.61 grams of hydrogen. Now we need to convert each of these mass quantities to molar quantities if we're going to find our empirical formula. So we're using the atomic mass for each. All right, now we have some numbers to crunch. So 80.21 divided by 12.01 is 6.679, I'll call it, moles of carbon. 10.18 divided by 16.00 is 0.6363 moles of oxygen. And then 9.61 divided by 1.008 is 9.534 moles of hydrogen. All right, now these are going to be all of the values for, actually, I should just open a new slide. These are going to be our values for our subscripts for our empirical formula. Now to find, we want the simplest integer ratio. So we are going to divide each of these by the smallest quantity and then move forward from there. Oh, and now we gotta open up some grab my calculator. We got 0.679 divided by 0.6363. So carbon is 10.497. hydrogen, let's see, 9.534 divided by 0.6363 comes out to be 14.98, and oxygen is 1. All right, so this is 15, right? 14.98 is 15. 10.49 is 10.5. That is 10 and 1/2, or 21 over 2. So we've got a fraction here that we got to deal with. So this carbon is 21 over 2. Hydrogen is 15. And oxygen is 1. We got to get rid of our denominator here. And multiply each of these values by 2. So our empirical formula comes out to be C21 H30 O2. So this is right here. Oops. This is the empirical formula. We still have to determine the molecular formula. And to do that, we need the molecular weight, which is right here. Right, because we need to find the ratio between the empirical formula and molecular formula. So we will need to calculate the empirical weight. So we have 21 carbons, 30 hydrogens, and 2 oxygens. So let's see. 12.01 times 21 is 252.21. 1.008 times 30 is 30.24. And then 16 times 2 is 32. So adding these all up together, 252.21 plus 30.24 plus 32 adds up to be 314.45. This is the empirical weight. Now we need to find a ratio between the empirical weight and molecular weight. So you go molecular weight over empirical weight. Molecular weight is 314.47. Empirical weight is 314.45. So that ratio is 1. So for this problem, the empirical formula is the molecular formula because that ratio is 1. So the molecular formula here is C21, 21 H30 O2. Alrighty, so that is the answer for that problem. It is now 4:01, so I got to run. I have a 3-year-old I got to wake up from a nap. But thanks to everybody for coming out. It was an awesome office hour, questions the entire time. I'll catch you all next week, same time, same place. Later.